Analog presents Visions of the Future with Isaac Asimov. The line between science fiction and true science is often thin and sometimes difficult to define. Yet there is a line between fiction and science. It is as fine and clear as the boundaries separating the Cretaceous from the Tertiary, the age of dinosaurs from the age of mammals. The only difference is that our boundary is constantly moving as science redefines science fiction. The dreams of just a few years ago are today's commonplace events. It is this boundary that was the lifelong fascination of Isaac Asimov. The mission of this video series is to examine that boundary, that moving target. Isaac Asimov launched this video project 2 years before his death. It synthesizes his visionary concepts with his scientific roots. This first volume contains the highlights of his last major interview and serves as both a mission statement and a tribute to one of the greatest science and science fiction writers ever known. Isaac Asimov, born January 2nd, 1920, died April 6th, 1992. 7 decades of brilliant wit, scientific insight, futuristic understanding, and absolute clarity. Isaac Asimov's literary output alone embodied over 500 volumes, including science, science fiction, mystery stories, limericks, history and humor, even guides to the Bible, Shakespeare, and Gilbert and Sullivan. Winner of numerous awards for both nonfiction and science fiction writing, Asimov was best known as the great explainer of science. His knack for making the complicated simple, the confusing clear, and the mundane exciting will never be equaled. In his lifetime, he entertained millions, but more importantly, he enlightened everyone about the world in which they lived. Blessed with total recall, Asimov became an encyclopedia of scientific information. Thousands of admiring fans wrote him each year, including young scientists and writers seeking his opinion and expertise. He responded to all inquiries. Martin Greenberg, Asimov's close friend and collaborator, confided that with all the letters written to Asimov each year, he kept only 3. These 3 letters speak volumes for the diversity of his readers and admirers. A letter from Dwight D. Eisenhower, one from Orson Welles, and the one that probably meant the most to Asimov, from Tommy Smothers. Born the son of poor, hard-working Russian immigrants, Asimov spent long hours as a child diligently working in his father's Brooklyn, New York, candy store. That work ethic imprinted on his young mind. As an adult, Asimov continued to write 10 to 12 hours a day, 7 days a week. When forced to stop for a brief time, a tiny voice within would implore, "Who's watching the store?" And the writing continued. But it wasn't really work to Asimov. Writing was his love and joy. Words flowed from his mouth with ease and clarity. No pain, no blocks, no anguish, just pure joy. When asked by Barbara Walters, "What would you do if you only had 6 months to live?" Asimov replied, "I'd type faster." A self-confessed genius, Asimov taught himself to read at age 5 and graduated from high school at age 15. He earned his Bachelor of Science degree and a PhD in chemistry. Soon after, he received his appointment as an instructor in biochemistry at Boston University School of Medicine, even though he had no formal courses in biochemistry, a fact that somehow eluded the university. No matter, his classes were the most popular on campus. But it was as a young boy working in his father's store that Asimov first discovered his love of writing and science. The arrival of 3 science fiction magazines, Amazing, Science Wonder Stories, and Astounding, caught the attention of his keen, inquisitive eye. With the help and tutorage of Astounding's editor, John W. Campbell, Asimov's fame as a science fiction writer was assured by age 22. Among his accomplishments, Asimov virtually created the field of fictional psychohistory with his immensely popular Foundation series. And he actually coined the term robotics with his classic I, Robot. One of the world's most prolific writers and the best-known modern science fiction author, Asimov's mark in science fiction history is firmly etched with such works as Pebble in the Sky, The Currents of Space, The Caves of Steel, The Gods Themselves, Foundation's Edge, and The Bicentennial Man. Yet with his incredible sense of clarity, Asimov was also able to bridge the gap into non-fiction science writing. A fascinating book on elements, Building Blocks of the Universe, and another on blood chemistry, The Living River, are but two of his award-winning non-fiction writings. In the end, illness and medication prevented Isaac Asimov from doing what he lived to do, write. And when he could no longer write, he died. Asimov once described himself as being, in an ascending order of importance, a scientist, a science writer, a science fiction writer, and the world's greatest lover. We think he'd like to be remembered that way. Join us now as we roam the universe through the incredible mind of one of our true national treasures, scientific visionary, Isaac Asimov.
My name is Isaac Asimov. I'm editorial director of Isaac Asimov Science Fiction magazine, and I've been involved with science fiction all my life practically. And the problem is, how do you differentiate between science fiction and science? And the answer is that it's very difficult to do so, because not only is the boundary fuzzy, but it changes all the time, and very rapidly sometimes, usually in the direction of science. And in this series of programs, what we're interested in is considering the immediate future, where we are going, and how it's going to affect us. Now, even the most ethereal advances have this habit of affecting us. For instance, so we do send out rockets into space. Some people might think it's only a scientific boondoggle. How is it going to affect us here on Earth? Well, stop and think a moment. Communication satellites mean that we can communicate all over the world instantaneously. Television is now distance insensitive because any television waves can go to a satellite and be reflected to some other point on Earth. As a result, anyone on Earth with a television set can see what's happening anywhere else on Earth. It has made our planet so much smaller. It has introduced us to the notion of globalism in a way that makes it practical. You couldn't have this sort of thing without the technological advances of the last few decades. And it may point the way to a future in which we can survive, simply because more and more we are thinking of ourselves as a planetary people. More and more we are thinking of the Earth as a small object. And therefore, we can work better on the problems that face us all, that are global in nature. In other words, all this, quote, science fictional, unquote, stuff about space travel has utterly changed our planet and ourselves, our way of looking at the world, looking at each other. And this is true in almost every other field, if not in quite every other field, of scientific endeavor. The advance of computers, for instance, the advance of new medical techniques, the recent discoveries in superconductivity. All these things are not just a matter of scientific curiosity, although that is frequently what drives scientists, but it also has all the opportunity of changing our lives. We have new medical techniques which can perhaps control human evolution. We can, instead of waiting for the hit and miss of ordinary evolution, have designed human beings. Now, this can be technologically possible, and yet there may be social problems arising. Supposing we can design human beings, how ought we to design them? Is intelligence that important? Do we want to have everybody double domes? Do you want everyone to have blue eyes or everyone brown eyes? So that we not only have to expect change, but we have to be able to control it a little bit. And in order to control it sensibly, we have to know in advance what's likely to happen. And the purpose of this program is to advance ideas and suggestions as to what is liable to happen, what is on the frontiers of science now, and how possibly we ought to react to it. When I began to write science fiction way back in the 1930s, or the Middle Ages as I like to think of it, that was a time when space travel was absolutely science fiction. Even a trip to the moon was science fiction. One of my first stories was about someone getting into a rocket ship and going around the moon and coming back. And boy, was that a stroke of imagination on my part. And now, long since, we've reached the moon in much more complicated fashion than I dreamed of in my science fiction. We've done much more. We live in a space-centered society practically now. We can't do without our satellites, communication satellites, our navigation satellites, our spy satellites. And the odd thing is that if we were only to go back 40 years and try to talk about it, everyone would sneer. The next logical aim is to reach Mars, and that requires a trip of perhaps a year and a half or more, so that in order to do that, we are not likely to be able to start from Earth itself. We are going to have to build space stations, which are in the works. We're planning them. On the space stations, people are going to work for indefinite periods of time, in shifts undoubtedly. And that will be the launching pad for long trips, the ones to Mars. And Mars is a different thing from the moon altogether. It's much more like Earth. It has an atmosphere, has polar ice caps, it's got the signs of ancient rivers and so on. We may discover a great deal about Earth by going to Mars. That's the point we must never forget. We're not just going out there to go out there. We're going out there to learn more about ourselves and our own world and our own lives. And we mustn't think of space stations as only a place from which to launch trips far out. We can also use it as a base for people to work in space over extended periods of time to build all the structures that we're going to need in space. Solar power stations to supply the Earth with energy. Maybe even places where people can live, tens of thousands of them, in space settlements, orbiting about the Earth. We can have really an extension of the human range by way of the space stations. One of the big problems of space is the energy it costs us. The rockets we use now are extremely primitive, use incredible amounts of energy in order to do comparatively little. And we have to wonder, is there any way we can make long trips without concomitant increases in the amount of energy we use? And one of the possibilities is to go back to sailing ships. You know, in the old days before we ran ships on steam, on burning oil, we used the wind. And it blew into the sails. Silently and without energy expenditure, drove the ships over the ocean. And now we have another kind of wind, a wind that comes from the sun, a series of particles always driving outward. And if we had sails large enough, this solar wind could push us here and there. And there are ways of doing such a thing which would save greatly on energy, but which would require other great advances, because you would need sails that were many square miles in area and yet were comparatively light. but we have the vision of the clipper ships of the future sailing through the solar system. And we have to realize just exactly how large the universe is. The moon is only 250,000 miles away. Jupiter is 500 million miles away. Pluto is 2 to 4 billion miles away, depending on where it is in its orbit. And the nearest star, Alpha Centauri, is 7,000 times as far away as Pluto is. Light, which travels faster than anything else in the world, 186,282 miles each second, takes 4.3 years to reach Alpha Centauri. And Alpha Centauri is the nearest star. Our Milky Way galaxy is 100,000 light years from end to end. The Andromeda galaxy, the nearest large galaxy to us, is 2.3 million light years away. The nearest quasar is 1 billion light years away, and we have been studying objects that are up to 16 or 17 billion light years away. It's very unlikely we'll ever be able to cover such vast distances. It may even be difficult ever to reach just the nearest star. But if we can't go there, they, in a sense, can come to us because we receive light from all parts of the universe, even the farthest. And the difficulty is, of course, that in the first place, some of the light is dim indeed when it comes long distances. And in the second place, it must penetrate our atmosphere, which absorbs and distorts some of the light and other radiation that ought to reach us. For that purpose, scientists have long dreamed of a large telescope in space which can observe the universe from outside our atmosphere and see things much more clearly and sharply. One of the things we're looking for through the Hubble Space Telescope is just exactly what the universe looks like very far away, billions of light years away, because it takes light billions of years to reach us from those distant places, so that we're seeing light and objects as they were not long after the universe came into being. We may be seeing objects as they were only 1 billion years or so after the universe was first formed. Now, we don't know much about the early stages of the universe. If we can find out more about it through the Hubble Space Telescope, we'll know more about how the universe developed to its present state from its origins and where it might be going in the future. In short, it's going to be telling us a little bit about where we came from and where we're heading. Furthermore, there are many objects in space that the Hubble Space Telescope will be able to see more clearly inside of, so to speak. For instance, there are globular clusters that contain 100,000 stars in a almost tightly packed ball. To us, from here on the surface of the Earth, it's just a blur of light. But through the Hubble Space Telescope, we may be able to see into the interior of the cluster, or into the interior of some of the centers of the nearer galaxies, and perhaps be able to see if, as we think, there are black holes there. We'll learn more about black holes, and again, who knows what this will tell us about the universe as a whole. We can make sharper measurements of the positions of stars, be able to tell more accurately just exactly how they're moving, how fast, in what direction, and from that, be able to understand what the circulation of the stars is in our Milky Way, and therefore how our sun is traveling through it, and be able to find out just exactly how the galaxies are moving, how the universe is expanding. It may give us discoveries that we can't imagine now, simply because we've never seen anything clearly enough to make those discoveries. It's impossible to predict what they will be. That's one of the great excitements of science, that always there is the unexpected. Always there is something that no one thought of that completely revolutionizes our thoughts in this direction or that. It's a kind of excitement that keeps scientists going, I assure you. And if the population generally can be made to share in it, how much pleasure they will have. Perhaps the most revolutionary development of recent years has been that of the computer, because for the first time we've discovered a machine that can substitute, at least in part, for the human brain. Before that, it was just a matter of saving human muscles, of using machinery to spare what human muscles couldn't do very well. And computers come in all sizes because they've been getting smaller and smaller. We've got these tiny little microchips now. And as a result, every industry, the government itself, tax collecting agencies, airplanes, everything depends on computers. We have personal computers in the home, and they are constantly getting better, cheaper, more versatile, capable of doing more things, so that we can look into a future when, for the first time, humanity in general will be freed of all kinds of work that's really an insult to the complex human brain, that requires no great thought, no great creativity. Leave all that to the computer, and we can leave to ourselves those things the computers can't do, such things as imagination, creativity, fantasy, intuition, problem solving, where we don't have to have the exact conditions and know exactly what's happening. We have an intuitive feel for what the solution ought to be. No computer can do that. And we can save our own brains for that purpose. Artificial intelligence is a phrase that we use for any device that does things which in the past we have associated only with human intelligence. For instance, if you have a machine that can alphabetize cards very rapidly, until recently only human beings could alphabetize cards. In that case, you've got an example of artificial intelligence. But this does not necessarily mean that something that is artificially intelligent thinks, quote unquote, precisely as a human being does. It may be a completely different kind of intelligence. The machines may specialize in certain, quote, mental activities, while human beings specialize in others. We do a great many things we're not good at. For instance, we're not really good at arithmetic. We need help. We need numbers, we need pen and paper, we need devices. Well, the cheapest computer in the world can multiply and divide faster and more accurately than we can. That's its specialty. Our specialty is different things. So that you end up not having artificial intelligence and natural intelligence identical, but two different things, two different specializations. They work together. Each supplies the lack of the other. And in cooperation, they can advance far more rapidly than either could by itself. Furthermore, computers are not just immobile things, because you can hook computers up to machinery and have the machines that spare human muscles also act in such a way, in such a versatile way, that they seem to be thinking. You have artificial intelligence applied to machines, and we call them robots. In science fiction, you always think of robots as man-like metallic creatures. But actually, any machine that's computerized is a robot. And we have industrial robots right now that don't look the least bit like human beings, and yet that do things that until just a couple of decades ago, only human beings could do. And we're going to live in a future, perhaps, in which we will have personal robots as well. Robots that do look like human beings and that replace, for the first time, what we used to call servants and free us all. For the first time, we're going to be free, really, truly free, humanity as a whole. Now again, what's life going to be like if we are completely computerized and completely robotized? What are the side effects? Will there be difficulties? Undoubtedly. Will there be things that we won't like? Undoubtedly. But we've got to think about it now, so as to be prepared for possible unpleasantness and try to guard against it before it's too late. We always have to do that. It's like in the old days when the automobile was invented. Would have been so much better if we had built our cities with the automobile in mind, instead of building cities for a pre-automobile age and finding we can hardly find any place to put the automobiles or to allow them to drive. This is the sort of thing that we must avoid in the future. The crucial compounds in living tissue are the genes, which are made up of a substance known as deoxyribonucleic acid, or for short, DNA. These are the blueprints of life. In every living cell, there are DNA molecules, each one of which controls a particular enzyme, and each enzyme controls a particular reaction. And all the reactions put together are what makes the cell be what it is and do what it does. Human beings have genes, corn plants have genes, whales have genes, bacteria have genes. The genes differ from species to species. And for 3 billion and more years, they have been developing, they've been reproducing themselves, occasionally making mistakes, so to speak, mutations, so that new forms of life with new kinds of properties develop, and natural selection chooses among them, so that we evolve. We've come from originally just bacteria-like creatures to human beings and whales and giant sequoia trees. Well, how long will it take for changes to continue in the future? And the answer is a good long time if all we depend on is just the usual hit and miss, the usual randomness. But we have learned how to identify genes, how to determine their structures, how to determine their position inside the chromosomes of the cell, how to modify and change them. And we've been working on this in practice in such things as bacteria and plant cells, and devising creatures with new properties. We have arranged to have bacteria prepare human insulin, for instance. Well, what's going to happen as we improve our ability to do these genetic engineering things? Why, we might be able to direct human evolution. And as a matter of fact, right now, we are in the early processes of determining the human genome, which means the position and structure of every one of the many thousands of genes in the human chromosomes. This is an enormous project. It's one of the big science projects. We can't tell how long it'll take us, but once we know exactly where the different genes are and what they do, we may be able to eliminate these inborn diseases of metabolism that you're born with, be able to correct them. We may be able to sort of alter human beings in one direction or another. This raises enormous questions as to what we want to do, because even if we can change human beings, in what direction do we change them? Do we want to change them this way or that way? This is an example of the way in which technological advance impinges on sociological necessity, and where the question always arises, must we do something just because we're capable of doing something? Or can we withhold our hands and say, no, this is not a good thing to do? Or if we do it, this direction makes sense, that direction doesn't. This is something that the human species must decide for itself. You and I, we can't just leave it to the scientists. And in order for you and for me to make the proper decisions, we have to know what's going on and why. And that's another purpose of this series, to help us understand what science is doing so that we can help direct it. Electricity pours through conductors, usually metal wires, but it doesn't do so completely efficiently. Some of its energy is turned to heat, and you only get a certain amount of it that can do the work. If, however, you make certain objects very, very cold, close to absolute zero, it loses all resistance to electric currents. The current then flows through without any loss of energy, and all of it can be turned into work. The only catch is that such superconductivity only seemed to exist very close to absolute zero, say within 20 degrees of it. And although for years, for something like 70 years, we tried to find substances that were superconductive at higher temperatures, nothing ever worked until just a few years ago, when they suddenly found that certain ceramic substances were superconductive at much higher temperatures. And now there's a great push to try to figure out what ceramics will give us the highest temperatures for superconductivity, still low, but higher. And how you can take those ceramics, which are very brittle substances, and learn how to make the wires out of them. Because if we could have, quote, wires, unquote, which conduct electricity without heat loss, we can make electricity do 2 or 3 times as much work as it does right now. There are various other things we can do with superconductivity too. Build still smaller computers, still more rapid computers. We can perhaps use it to create nuclear fusion and give us a completely new source of energy. And it might become possible to create magnetic fields which can be repulsive, which can push things away, so that we have trains, let us say, rolling along a metal railing, perhaps 1/10 of an inch above it, held up by a magnetic field created by a superconductive current, and there's virtually no friction. And if you have it go through an evacuated tunnel with no air resistance either, it can go as fast as an airplane. And you get in, and in a matter of an hour or so, you find yourself going from New York to San Francisco, to say nothing of the fact that the energy we save can be used for other things. Ever since ancient Greek times, scientists have been speculating as to the ultimate structure of matter. What is it that makes up all the various things we see about us? Things that are so different: water, metal, living things. Surely there must be something that makes them all up. And we've worked our way down to atoms. By the beginning of the 1800s, we understood atoms. By the beginning of the 1900s, we understood there were still smaller particles inside of atoms. And since then, we've been trying to investigate these small subatomic particles in order to find out just exactly how they fit together and build up the structure. And the only way we can do that is to smash particles together and observe what happens in the debris that it produces. It produces all kinds of other particles out of the energy of the smash, because, of course, energy and matter are interconvertible. And we have discovered, for instance, that apparently the fundamental particles, the ones that can't be broken down any further, are 6 leptons and 6 quarks. But one of the quarks is still missing. It should exist in theory, but we haven't located it. In addition, there are certain other particles that make it possible for different particles to interact with each other. And one of them is the Higgs particle, so-called because a physicist named Higgs pointed out it ought to exist. And we haven't located that either. And so we need more and more energy to smash particles together more and more sharply and more energetically. And in fact, they're talking about the super collider, which would be a evacuated tube miles and miles across, in which the particles can be circling and circling, going faster and faster, getting more and more energy until they finally smash together. And we'll see if perhaps we can detect the missing particles and who knows what else. Now, not only is this a matter of scientific curiosity, but it's liable to explain to us, for instance, how the universe began. Because when the universe first started, there was a tiny little object, enormously high in temperature. its properties completely different from the universe we now have. We might be able to understand it if we knew more about the ultimate products of matter. And in addition to that, there's every indication that some 90% of the universe we cannot see or sense in any of our instruments. It's called the dark matter because it doesn't glow, it doesn't give off any radiation, and we have no instruments that detect it. If we knew more about the ultimate construction of matter, we might be able to understand what the dark matter is and learn how to study it, and learn about 9/10 of the universe that we know nothing of. And it'll tell us how it developed, where we're going, where we came from. And again, we have no way of knowing how that will help us in our own technology. I mean, when we discovered the electron in 1895, it seemed to be just a scientific curiosity, a tiny little particle that was inside atoms and nobody cared except a few scientists. Except that out of it grew the great electronics industry. Without the electron, we wouldn't have radio, we wouldn't have television, we wouldn't have recording devices, we wouldn't have almost anything we now have and take for granted. And we don't know what further discoveries may tell us not only about the universe, but about our own technology.
Isaac Asimov's Visions of the Future has given you a preview of the subjects and issues the analog science fiction and fact video series will be all about. Look for future videos that will be out soon.